quantumlaserpointers.com.
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
Now, blackbody radiation is a very interesting and powerful idea, but moreover it can be understood with relatively simple ideas. So let us begin with a nice thought experiment. Imagine a box floating in space far away from anything, out there in the vast nothingness of space. Now recall that throughout all of space there is the light radiation left over from the Big Bang. It is this that we measure when we look at the cosmic microwave background radiation. So as the box is there floating out in space, some of the leftover light will be falling on the box and hitting it. The box can either reflect the light or it can absorb the light radiation. Now a black box will absorb all the light that falls upon it, and that's what makes things seem black. They reflect very little light and absorb all the light that hits it. Now a white box, or one covered in mirrors, would reflect all of the light. So now let's consider that black box. The cosmic background radiation will be falling upon it constantly, being absorbed and heating up the box. Now the temperature of the background radiation is about 3 Kelvin, so if the box is about 3 Kelvin, then what would happen? Will it still continue to heat up? Like I said, radiation will be falling upon it and heating up constantly, and if it doesn't have a way of cooling down, then it will heat up forever, without any good way to cool off. Then given enough time, it will become hotter than the sun. This really doesn't seem right, so we need some kind of mechanism to cool off the box, because the radiation will just continue to heat up the box. Well, in everyday life, something hot leaks its heat out into the surroundings, into the air and into objects that it's touching. But in space this can't happen because there's nothing to transfer the heat to. But there is something that easily propagates through space and carries energy. Light radiation. And light carries energy, and every single wavelength carries a different energy. So we can suggest that this is how the box will try to keep at thermal equilibrium with its surroundings. That is, to stay about the same temperature. Well, with this in mind, let's try and consider how we can cool the box down with this idea. We could have it emit light of all wavelengths and energies, with different amounts of each wavelength to carry heat away. This leads to the idea of a perfect black body. A black body will absorb all radiation that falls upon it, otherwise it just wouldn't be black. But as a result it must perfectly emit all radiation too, otherwise it would just heat up. Now this is an interesting idea, but it seems a bit weird. But you can see it for yourself at home if you have anything that uses electricity to heat up objects, electric grills, electric heaters. If you leave it on for a while you see it starts to glow red. This is because it is emitting red radiation to cool off, and so to stay at a thermal steady state. Similarly, if you see a lump of coal in fire, it glows red. This is again because its temperature is quite high, and so it's emitting radiation to cool off, and enough red radiation is being emitted to be seen. This is also the idea behind how thermal imaging works. An object will emit radiation related to its temperature, and thus, things about room temperature mostly in the infrared spectrum. As things get hotter, they will eventually emit most light in the visible spectrum, and if they get hotter still, they will mostly emit ultraviolet radiation. Going back to electric heaters, a black body emits enough red radiation to be seen at about 600 Celsius or about 900 Kelvin. Temperatures far above what we see in everyday life, so it stands to reason we don't normally experience black body radiation. Now, a physicist called Max Planck found a way to describe how much light radiation is emitted from a hot object, but more importantly, how much energy of light is emitted for a given temperature. So let us briefly look at a graph and discuss the properties of it, and try to see what they also mean. This way we can get a better understanding of what blackbody radiation actually tells us. You may want to recall that the energy of a photon is proportional to the inverse of its wavelength, so that the smaller the wavelength, the larger the energy, the smaller the energy, the longer the length. Now, visible light has a wavelength of about 0.4 to 0.7 micrometers, which is a very small part of the spectrum as shown. You can easily see that we cannot see a lot of the light emitted, especially at low temperatures. Next we can see that for low wavelengths, that is, very high energies, very little light is given off beyond the peak, with a very sharp fall after the peak, especially when the objects are very hot. Whereas at low temperatures there's a smooth curve going down. Another important point is that as the temperature gets hotter, the peak moves to shorter and shorter wavelengths. That is, the object starts emitting most of the light at really, really high energies. This point is important because it will come back to prove very useful later on. We can also see that for higher wavelengths of light, there is a slow decay towards nothing being emitted. And no matter what the temperature is about, the same amount of low energy light is emitted. Also, the peak gets sharper when we increase the temperature. This is why we can see red at about 600 Celsius, even though its peak is still well before red, which is about 3000 Kelvin. The peak is wide enough that red light will have enough emission even below 300 Kelvin to be picked up in the dark. Finally, the total energy emitted is proportional to the area under the graph, and we can notice that this increases as the temperature increases. This fits with our idea of a black body emitting enough radiation not to really heat up. Okay, now you may be thinking that why have I wasted your time with this, and why have I called it a powerful tool, and why is this even important? Well, let's give an example of just how useful black body radiation is. Stars. If you were to look at the emission spectrum from a star, you'd see that its curve approximately matches that by Planck's black body formula. And so we can model stars as black bodies. Let us try this with the sun. We can look at its spectrum and see that it's about 6000 Celsius. Then if we go and measure the temperature of the sun, we find the same thing. It turns out it's about 5778 Kelvin. Close enough. Moreover, this explains why the sun is white. Its peak is in the middle of the visible spectrum. The visible spectrum is about 400 to 700 nanometers. And so, because it's at a lowish temperature, its peak is wide and it emits a lot of light across all the visible spectrum. And so we see all the colours of visible light. And as a result, it appears white. So let us take a brief detour and think about what we can do with this in other fields of science, and I'm going to consider evolution. If an eye wants to be able to see at its best, then it needs to take advantage of the main source of light around it. In everyday life, that would be the sun. But the sun emits most of the light around its peak. So if an eye was to evolve to use the sun, it makes sense that the peak of the sun be in the middle of the visible spectrum. If not, our visible spectrum would shift, such that the peak is now in the middle. This allows us to formulate a hypothesis that if life was to form around a star with a significantly shifted peak, if it was to evolve some eyes, they would see around the new peak spectrum. Now back to physics for the final run. With this new knowledge of blackbody radiation, we can look at the main sequence stars far away and see what colour it appears, and then we can work out its temperature solely from its colour. 61 Cygni A is red, and so its temperature would be about 4500 degrees. Whereas Pi Andromedae is blue, and so we expect its temperature to be about 15,000 Kelvin. If you don't feel like this is impressive enough, well, from knowing how hot it is, we can also work out how much fusion is needed to take place in order to keep it at this temperature. And in order to have this much fusion, we can then work out how much mass has to be there. The final consequence is that we then know how big the star is. If you think this is interesting and you would like to know a bit more about it, then you should look up Hertzsprung-Russell diagrams. One of them is shown. What it does is show how this can be used to classify stars using the size and the temperature, the colour, to be able to say how big, how bright, what type of star any star is. Finally, the last thing I want to just briefly touch upon is how this is related to quantum mechanics. Max Planck came up with a solution to blackbody radiation, whereas classical mechanics could not predict it. Classical mechanics can only deal with the low energy part of the emission, but not the high, and this was known as the ultraviolet catastrophe. In order to fix this, Max Planck suggested that light was emitted by the atoms in a blackbody in small packets of energy called quanta, which then went on to become known as photons. This is a radical difference from classical mechanics, which predicts a continuous emission of energy, not just in small discrete packets. And this was one of the first pieces of evidence for quantum mechanics, as it relied upon energy coming in discrete packets of energy, a central concept to quantum mechanics. Secondly, if we were to look at the emission spectrum for the sun, we can see that the actual emission is very shaky. This is to be expected as the sun isn't a perfect black body, but there are wavelengths where the intensity seems to drop a lot. These are from quantum mechanical effects and lead to some of the best evidence for the current model of the atom. Thank you for listening. Please let me know what you think. And for my next video, I'm either going to take a small departure into basic population dynamics or into the meat of quantum mechanics yourself. If you have any preferences, please let me know.